Oh, you have the mic. Right. Yeah.
Okay, so I will talk about a new width parameter, which I call multi-clique-width. So it is related to the well-known width parameter clique-width, which has been preceded by tree-width, which naturally is by far the most important width parameter. So because I will talk about the relationship between these parameters, I have to remind you a little bit about tree-width and clique-width. But why do we use tree-width? Many combinatorial graph problems are NP-hard, but usually they are not only easy for trees, but for graphs of bounded tree-width. And we always have efficient algorithms that use dynamic programming bottom-up in the tree decomposition. So for the definition of tree-width, to remind you, I just use this example. I say so on the left side you have a graph, and here we have a tree decomposition. So every vertex like this one appears in a connected subgraph of this tree, and for every edge like E and G, they have to appear somewhere in one node here. And the width of the decomposition is just, traditionally it's one less than the number of vertices, the maximum number of vertices that you have in a node. And choosing the best possible such tree defines the tree width. We are concerned with fixed parameter tractability, so we always want to solve problems in such a running time polynomial in n, the size, the number of vertices of the graph, but there is a factor which is an arbitrary computable function of the parameter. In our case, the parameter would be a width parameter. So many NPR problems are fixed parameter tractable with respect to tree width, but also with respect to clique width. Clique width is a much more generally applicable parameter that many graphs of unbounded many classes of graphs with unbounded tree width have still bounded clique width. So I have to review the definition of clique width a bit more closely. So clique width is defined with the help of K expressions. So the idea is graphs of bounded clique width don't have to be sparse. We have efficient algorithms because they are constructed in a kind of simple manner. So we have K labels. Every vertex has a label, and then we have these operations. We can create a vertex with a given label. We add edges between all pairs of vertices where one has label I and the other one label J. We can change the labels from I to J, and we do disjoint unions. And the clique width is then just the smallest number of labels that allow us to produce the graph. And efficient algorithms are obtained by dynamic programming on the parse tree of the K expression that produces the graph. So I said before, tree width and clique width are somewhat related. Tree width can be very big, even if the clique width is small. A complete graph is the extreme example. Clique width is just 2, tree width is 1. But in the other direction, we have bounded tree width implies bounded clique width. But this result is not trivial and somewhat complicated and somewhat unsatisfying, because bounded tree width implies bounded clique width, but there is an exponential blow-up. So we have an exponential upper bound and an exponential lower bound. There are many graphs where the clique width is exponentially bigger than the tree width. And this is unsatisfactory to me, because clique width is kind of supposed to be a generalization of tree width, allowing fast algorithms for a larger class of graphs. And so we have this complicated relationship and this exponential blow-up, and we want to understand this relationship better. And so I propose to study a width parameter which I call multi-clique-width, and it's almost the same as clique-width. The definition is almost the same, sorry. With the one exception that we allow every vertex to have as many labels as we want. So we have k labels, and every vertex can have any subset of these k labels. And then, so the definition is just as natural as that of clique-width, just allow many labels instead of one. But the notion of multi-clique-width is now much more powerful, and it's still easy to use for algorithms. And naturally, we still have bounded tree width implies bounded multi-clique-width, but this time we have no exponential blow-up at all, so it just adds 2. To it, and actually the proof of containment is very, very natural. One just uses these k labels to remember which edges have still to be added later on in the construction. And the relationship between clique width and multi-clique width is quite easy to see. Naturally, we can always introduce one label for every set of labels, so very often the clique width is actually exponential in the multi-clique width. And I already said. So that's one of the important properties of multi-clique-width. The relationship to tree width comes very natural without this blow-up. And the other important property is that we still have many algorithms that are as efficient in terms of the multi-clique-width parameter as they are in terms of the clique-width parameter. So that means that they are actually, on many graphs, they are exponentially faster. And for that, I just look, in the proceedings, I look at 2 examples. Here, I'm just looking at one example, independent set polynomial. So it's just a problem that contains the problem of computing maximum independent sets. It is a bit more general, and namely, here I even count the number of independent sets of each size. And one can easily express these numbers if one looks at this independent set polynomial, where the coefficient of x to the I is just the number of independent sets of size I. And in order to compute it efficiently, I use this auxiliary polynomial where, I have basically the same thing there. But I subdivide each coefficient. And namely, I don't just count the number of independent sets of a certain size, but the number of independent sets I look here at the number of independent sets of size I with the property that we are, for each label we say whether there is at least one vertex with that label in the set. And as I said, once you have defined this auxiliary independent set polynomial, it's actually very easy to compute it bottom up. Going through the K expression that defines the graph, computing the polynomial for the graph generated by a subtree, where one can easily compute it step by step, the way up. And yeah, so yeah, okay, so here I say quickly what has to be done, but yeah, I guess I'm running out of time. So we have a width parameter, multi-clique-width, is proposed with these two advantages. Generalizes tree width without an exponential blow-up, and so some interesting applications are still very, very fast in terms of this parameter. And naturally, most interesting problems are still open. We don't know how to compute efficiently the multi-clique-width. And another open question is how many such applications like independent sets do we have where this parameter is actually helpful? Yeah. How often is clique width much bigger than tree width? Clique width bigger than multi-clique width, sorry. Yes?
Are there any examples where you know of a fixed of an algorithm which is fixed parameter tractable for clique width but not for multi-clique width?
I mean, bounded clique width is equivalent to bounded multi-clique width. Right, so it's fixed parameter tractable in one case if and only if it's fixed parameter tractable in the other case. So the question is what that function is. Does it blow up exponentially or not? Yeah. This is, no, I certainly have no proof that anything does not work. But on the other hand, it also does not seem to work all the time.